Dan, new name. You got a new name, Dane. Dane began surveying in 2005, and on day one, he knew he was a surveyor at heart. He loved the ability to be outside, perform historical research, perform mathematical computations, such as tonight, meet landowners, cut line, investigate, and assist with legal matters, and learn new equipment and technology. Dane received his land surveying and training certification in 2007, subsequently became a professional land surveyor in the state of Maine in 2009. Dane is currently not only licensed in Maine, but also Vermont, Texas, Colorado, and Oregon. In all, he's gained over 15 years of experience working in not only many different states, but also many different survey disciplines, including residential, commercial, ALTAs, the energy sector, transportation, construction. Dane currently works as a professional land surveyor for Colorado Department of Transportation. So I appreciate you always taking the time for us at least once a month, and tonight is no different. So I will turn it over to you, Mr. Dane, for some conversations on quadratic equations.
Yeah, I appreciate it. As always, I'm always here to help try to fill in something. So
I love it. Thank you.
Always keep me in mind. I'm trying to do my part. Yeah, so like you said, I'm a licensed surveyor. I live in Colorado, and I put together a manual and some training videos with Western Federation of Professional Land Surveyors, and it's been going really well. So if y'all ever have any questions, please reach out. I routinely put on study groups locally around here for a bunch of local surveyors. It started out just my own group here at Colorado Department of Transportation, but then it kind of grew and morphed into old connections and their LSITs and all their staff trying to get licensed. So that's a revolving door of people. I always make sure that everyone knows that there's no pressure, and they just come. And I actually like it whenever they tell me, hey, I don't understand what is standard deviation, or something like that, something to give me something to go on, then I can kind of build a quick hour or so lesson for them. So that actually happened with quadratic formulas not that long ago, quadratic equations. That's kind of how this came about. But I thought it was a really good question that someone asked, because whether we know it or not, these quadratic formulas, they're the basis for, they're the foundation for a lot of the math that we do as surveyors. So if you get a good understanding of what they are and how to break them down, I don't think it's going to hurt you. I don't think there's going to be a problem on the FS exam that says, hey, what shape is the quadratic graph of this equation? I don't think it's going to be that specific, but like I said, it's the underlying math behind a lot of what we do. So I thought it was good to try to explain what I know about them, and hopefully it helps y'all. And I'm not an expert. I'm not a mathematician by any stretch. So if y'all have any interjections or anything, please let me know. All right. So what is a quadratic equation? I like to think of the analogy of you throwing a ball up in the air. Okay. So you're going to have a ball, and you're going to throw it up as high in the sky as you can. It's going to have a little arc to it, right? The second it releases your hand, it's going to be going the fastest that it's going to go on its journey until the mirror image of its return back to the ground. Okay. So another way to think about this is you throw the ball up, it's going 80 miles an hour, let's say. Okay. As that ball travels up into the air, gravity is going to be pulling down on it, and it's going to slow down to a point where it reaches the climax of its height, and that's going to be the speed of 0. And then it's going to travel back down, and as it goes back down to Earth, it's going to be gaining speed. What is it, 9.8 meters per second squared or whatever, back down until it comes back down to Earth. And when it hits the ground, it's going to be going as fast as it was when it released your hand. Okay. So what you have there is a mirror of the half of the arc when it's accelerating into the sky. And then you have the other half of the arc when it's accelerating back down to the earth. Okay. So that in a nutshell, that's kind of what these quadratic equations represent, is an ever-changing first half of the curve, and then a mirror of the second half of the curve of what occurred on the first part. Okay. As by definition, the quadratic formula is always going to have something squared. Okay, because once it's squared, let me see, quadratic equations are used to find the curves on a Cartesian graph. So by definition, x squared would represent a quadratic formula. Okay. So you're going to have that squared element in there for it to meet the quadratic equation requirement. So the stereotypical quadratic equation format that we see is, I'm going to start right now, Trent, is you're going to have 3 parts of this thing. Well, actually 4, because the quadratic equation is going to equal 0, because the way I think of it is nothing is really obtained. When that ball is thrown up into the air and it reaches the pinnacle and it comes back down, nothing is really gained in this. Okay. You start and you stop at the same speed, right? So whatever we do in this equation, we're going to be equaling 0. Now, the other 3 parts of this, you're going to have your A, your B, and your C. The A part is going to have your squared variable. The B part is going to have the whole variable with, there's not going to be any square. And then you're going to have your whole number as part C. All right. Notice there's only one variable involved in here. There's no Y, there's no Z, there's no A, B, C. You just have your one variable, squared, not squared, and then your whole number. And each part of this trio, they're going to have a sign associated with them, plus or minus, plus or minus, plus or minus. All right. And those plus signs and these values of A, B, C are going to determine the shape of your graphed out quadratic equation. And that's what we're going to get. I'm going to go through that right now.
Hey, Dane,
yeah.
For those that are on, Dane has 2 screens. One is his overview, which has he's got the notebook paper, and you can pin that one to your screen as well. I don't know if everybody's seeing his 2 screens there or not, but I want to make sure that everybody's kind of following along with his hand graph here on the paper. So you can pin that other one, and then there's actually a view option at the top where you can do like side by side, which I'll have PowerPoint, and then his notebook paper on the other side. So just let me know if you can't figure that out, but go for it, Dave. Sorry.
Yeah, it's all right. And I'm not going to be looking at chat during this, so if just let me know if a question pops up.
Yep, no worries.
All right. So here's our 3 components, and we're going to go through and explain how these define the shape and direction and all the characteristics of this quadratic formula. Then we're going to go into some examples. Okay. So this is the typical quadratic form. Then the other aspect of this is going to be the roots form of the quadratic formula. Okay. And I took the time to go through and explain how you get from the typical format to the roots form of the quadratic equation. And I'd like to go over that a little bit. If nothing else, it's going to help us fine tune our PEMDAS skills, parentheses, exponents, multiplication, division, addition, subtraction. So I sat and I did it, and I just to know how to do it. And then after I did it all, I wanted to make sure everyone else understood it as well. So that's what this is right here. So we start out with the typical format. Ax squared plus bx plus c equals 0. All right. The first thing we do is we're going with the whole object of this is to isolate x. What does x equal? Okay. We're gonna carry every other aspect of this equation over to the other side of equal, and we're going to be left with x equals something. All right. So that's our goal here. First step is we're going to, you got to think of an equation, the equal sign, whatever you do to one side, you got to do to the other, right? It's a mirror image. And the function that you're trying to get rid of, you use the opposite of. So if it's plus c equals 0, you're going to subtract c from each side, right? When you do that, c's on the left-hand side are going to cancel out. And what we're left with now is ax plus bx equals negative c. Now, the next step is they're going to isolate a. They're going to bring a over, all right? The way they would do that is multiply each side by 1 over a. And when you do that, the a's here cancel out. I'm on my blue screen now. My a's here would cancel out, so I'm left with x squared plus b divided by a x equals negative c divided by a. So all I did was I multiplied each side by 1 over a. Now I have parentheses here, so I have to disperse this negative 1a to this component and this component. What we're left now with is x squared plus b over a x equals negative c over a. This is the part that I don't truly understand. If anyone can fill me in, I'd be more than willing to let them talk. But it explains it as the coefficient of the linear term needs to be divided by 2 and raised to the second power. So what they're trying to do now is they're trying to get rid of this b divided by a so that we only have x's over here, right? So in order to do that, what they did was they did just what they said. They divided by 2 and they brought it up to the second power. So they took that a divided by b, divided it by 2. If you look over here, divide by 2 to the second power. When you do the math for this, you're gonna let me see, it goes, the end result is b squared divided by 4a squared. Trying to see how they went from here. Let me think about this. Oh yeah. You divide the 2 by b and 2 by a. I'm sorry, you divide the b divided by a divided by 2. That's going to be the equivalent of b divided by 2a squared. So what you're left with is this b squared 4a squared. So we can replace this b divided by 4 with this, okay? When we do that, if I want to add it to each side to get rid of it now, it would become, I would multiply each side and it becomes, trying to find the next step here, x squared plus b divided by a squared x plus b squared divided by 4a squared, which is what we had here, equals negative c divided by a times 4a. No, I'm sorry. I want to backtrack here. Yeah, it should have been this line. Okay. Plus 4. So they're adding it to both sides is what they're doing. They're adding it over here and over here. Now, what they're doing in this step is they're trying to simplify it. Okay. what they're trying to get is this 4a squared. They want that on both sides so that they can then carry over this b squared plus 4a squared. So x squared plus b divided by a x plus b squared divided by 4a squared equals b squared minus 4ac divided by 4a squared. Let's go to the next one. All right, so this is what we're left with. Now, this is the opposite. What they have here, this right here, but I'm circling, they're gonna backwards FOIL. I don't remember. I mean, I don't know if you remember the FOIL system: first, outer, inner, last. So what they're doing here is x plus b divided by 2a squared. So what that really looks like is this over here, okay? So if you have this x plus b divided by 2a squared, that's going to be x plus b divided by 2a times x plus b divided by 2a, this right here, all right? And then you're going to, if you perform the FOIL system on this, it'll be first, so it'll be x times x, outer, which would be x times b divided by 2a. Then you would do inner, which would be b divided by 2a times x, and then outer, which would be b divided by 2a times b divided by 2a. When you do that system, you're going to get this right here, okay? Which is what we have right here. So all they did was backwards FOIL to get this, all right? So now we have this. Now we're at this point. To get rid of this square, we're going to take the square root of everything. When we do that, we're going to be left with just the innards of this equaling the plus or minus square root of all of this, which is what we have right here. Yeah, right here. Okay. So now we're almost there. We have everything. We have x simplified. So now we just got to bring this b 2a divided by 2a over to this side, which is what we're doing here. So minus both sides by b divided by 2a. And we're left with finally x on one side and everything else on the other. That everything else on the other is negative b plus or minus the square root of b squared minus 4ac divided by 2a. All right, so this was a long, convoluted way of explaining how you get from this typical quadratic formula format to this roots format, okay? And this is important because within this roots is going to be something called the discriminant. That discriminant is everything under this square root, this b squared minus 4ac, okay? So again, you do not know, you don't have to know how we got from this root, from the typical format to the root format. But no, what I do want you to try to remember is there is a process to get from there to here. And it's important because you're going to be left with this discriminant here. That's going to reveal something to us here in a second. All right. So are there any, I probably shouldn't ask this question, but are there any questions?
I'd say Jerry chimed in on the comments and nailed your reverse FOIL.
Yeah.
He nailed it by what way? Let me see.
The process is called completing the square. It allows using the square root to solve for both roots.
Okay. All right. That's reverse FOIL, I guess. Thank you, Jerry. All right. So I don't want this process to confuse you or to steer you away from what we're going to be talking about. All I wanted to do was show you how to get from one form to the other. Okay. And the importance of it is you want to isolate x on one side, and then you're going to have all your other components on the other. Okay. All right. So with that behind us, let's get into the real nitty gritty of this. Okay. So there's going to be four parts of this quadratic equation that are going to reveal to us the characteristics of our parabola. I was saying curve before, but it's not a curve. It's going to be a parabola. There's going to be a distinct climax point to this parabola. Okay. So the four components are going to be the discriminant, the a value, which is that x squared value, the b value, which is just the x value, and then the c value, which is going to be your whole number. So those are the four parts that are going to define and describe what your parabola is looking like, where it's located on the Cartesian graph, what its shape is. Is it, really shallow? Is it really sharp? Is it a U shape? Is it an N shape? Where is it? Is it on the right side or left side of the Y of the y-axis? Does it cross the x-axis? All that stuff is going to be described through these characteristics of these numbers. Okay. The discriminant, like I said before, is going to be the equivalent to what is under the square root in the roots form. So this b squared minus 4ac. All right. So let's take just the discriminant. First off, let me come up with an example here. All right. X squared plus 3x minus 4 equals 0. All right. Let's figure out what the heck that's going to be looking like. All right. The first part is the discriminant. The discriminant is going to be b squared minus 4ac. So the value of this, once I plug all these numbers in, is going to give me a number. That number is going to tell me something. And I'll explain what it means. Okay. So let's figure out what the equivalent of this discriminant is. So remember, this is the a value, this is the b value, this is the c value. Okay. So a in this situation is going to be +1. B will equal +3. And C will equal -4. So those are our values for A, B, C. Let's plug those values into this discriminant to see what it equals. So B is +3. So it'd be 3 squared minus 4 times A, which is +1, times C, which is -4. So what does that equal? 3 squared is 9. So it'd be 9 minus, multiply all these out. 4 times 1 is 4. 4 times -4 is -16. 9 minus -16, it's the same as writing 9 plus 16, equals 25, right? So our discriminant is +25. So now what does that translate to as far as a characteristic of what our parabola is going to look like? Well, if the discriminant is a positive number, we're going to have 2 real answer values. If the discriminant is 0, we're only going to have 1 real answer value. And if the discriminant is negative, we're not going to have any. We're only going to have complex numbers. So let's explain what all this means. in this situation, our discriminant is positive 25. That tells me we're going to have two real values. What is a real value in this situation? So you have your Cartesian graph, y-axis, x-axis. Okay. If you have a positive discriminant, that means your parabola is going to cross the x-axis in two places. It'll look something like this, or it'll look like this, or it'll look like that, or look like that, or that. All these parabola have one thing in common. They cross the x-axis at two separate locations. Okay? That's if it's positive. If it's negative, is your y-axis, x-axis. If you have a negative discriminant, that means it's going to cross your x-axis at only one location. Now, how could that be possible? If I have a parabola with two sides, how would it only cross the x-axis once? Well, it would only cross it once if the very top or the bottom of that parabola is on the x-axis. So it would look something like that, or that, or that, or that. It'll have the bottom part or the top part of this parabola will just barely touch and be tangent with the x-axis. That's if it's negative. And finally, if it's zero, if your discriminant is zero. If your discriminant is equal to a negative number, if we would have done this, and I don't know how to make it negative, but let's say it would have been let's say a value would have been -10. Okay, if a was -10, that would have made this -10. Well, no, that wouldn't have worked either. I don't know. I have an example coming up, but if I would have done all the math here and I would have got a negative number as my result, then the graph would look something like this. So I have my y-axis, my x-axis, and my parabola would not cross the x-axis. Whatever shape I would draw, it doesn't cross it. It might get close, it might not, but it will never make contact with or cross that x-axis. That's if my discriminant is negative. So if it's positive, it's going to cross it twice. If it's zero, it's going to just intersect it at one point. And if it's negative, it's not going to cross it at all. Okay? So this discriminant value is going to tell you that. It doesn't tell you the shape of this parabola at all. All it tells you is its general location. Okay? But you have no idea the scale of it, the shape of it, or its exact location. And we're going to get into what these negative values look like. So what that is explaining is, here's your y-axis and here's your x-axis. This parabola may not cross the x-axis, right? So it's a negative. My discriminant was negative in this situation. However, the mirror image of this parabola, if I make this parabola have a mirror image and flip it, its mirror image will cross the x-axis at 2 points. This discriminant had negative, right? Well, its mirror image will cross the x-axis. It itself doesn't, but you can create a mirror image of it, and that mirror image will. It would be impossible for it not to, right? And I'll explain that process when we get to that example. It's at the end. So that's the discriminant. The discriminant, in a nutshell, the discriminant tells you how many times this parabola makes contact with the x-axis. Okay. The next aspect is, back to our equation, x squared plus 3x minus 4 equals 0. All right, this was A, this was B, this was C. All right, let's look at the A value first. So we already did discriminant. Now we're going to do A value. A value is going to tell you the shape of this parabola. Okay, we already know the discriminant was positive 25, so we know it's going to cross the x-axis at 2 points, but we don't know the shape of it. All right, if it's a positive number, in this case it is, it's positive 1. If it's positive, it's going to have a U shape. Okay, it'll look like a smile. If it's negative, it's going to have a frown or an N shape. And that's how I remember it. Positive is someone that's positive is always smiling. Someone that's a negative person's always frowning, right? That's how I know it. Also, not only am I going to tell the shape, the value of this A will tell me how sharp or smooth the shape is, right? So if I have a huge, large value, if it was positive 9,000, my parabola would be really sharp and tight. Okay. If I have a value of positive 0.000001, it'll be almost a straight line, right? It'll be really smooth. So the larger the value, the tighter it's going to become. The sharper looking it is. The smaller the value, the wider it is. So in my mind, that's counteractive. You know, I think large number should be wide, but in this case, it's the opposite. And that's how I memorize it. A large number is going to create a sharp shape. A small number will create a large, wide, smooth shape. All right. So A tells us two things: the severity of this parabola, and is it a U or N shape? In our case, it's positive 1. So that tells me it's going to be a smile shape. And the value of 1 tells me it's just going to have a normal, it's not going to be too drastically sharp. It's not going to be too smooth. All right. So far, just by knowing my discriminant and my A value, I know it's going to be shaped something kind of like this. Okay. I don't know where it is. It could be over here. Could be over here. Yeah, I don't know where, but it's going to be a U shape, and it's going to not be too sharp, and it's not going to be too wide. Okay. So that's A. So now we've got discriminant and A. Discriminant was how many times it crosses X. A tells us shape and severity. Next, we go into B. What does B tell us? B is this value right here, the non-squared X value. In this case, it's positive 3. Positive 3. So B is going to tell us what side of the Y axis is the vertex of this parabola. The vertex is going to be the higher low point. Okay. Where does it change from going down to up? That's going to be your vertex. The B value tells us where this thing is according to the Y axis. All right. If it's positive, in this case it is, it's positive 3, it's going to be on the negative side of the y-axis. So kind of like the A, it's counterintuitive. If it's positive, it's on the negative side. If it's negative, it's on the positive side. So now I know one more thing about this parabola. I know it crosses the x-axis twice from the discriminant. I know that it is U-shaped. I know that it's not too severe and it's not too smooth. And now I know it's on the negative side of the y-axis. So it's going to be over here somewhere. Okay. So now it's going to be shaped something like this. Okay. But it could be right here. It could be right here. I don't know where it is, but I know that vertex is going to have to be on the negative side of the y-axis, okay, on the x. If it's negative, it's going to be on the positive side. So if this was -5, it would be over here somewhere. In this case, it's positive. If it's 0, that means it's perfectly centered on the y-axis. If my b value was 0, it would be, the vertex would be on the y-axis. It would be something like this. Okay. So B reveals the location of the vertex of our parabola in regards to the y-axis. Is it on the right side or the left side of it? Positive or negative? And then the final one is C. C is the y-intercept. So again, our formula is x squared plus 3x minus 4 equals 0. Our C value in this case is -4. So what does that tell us? Well, the y-intercept of our parabola is going to be at -4. Okay. So knowing everything now, I know what the discriminant is. Our discriminant was 25. Our A value was +1. Our B value was +3. And our C value is -4. Okay. So now knowing what all these represent, I can draw what our parabola is going to look like. I won't know the exact values, but I will know the shape and location of this thing. Okay. Discriminant, +25. Positive means it's going to cross the x-axis at 2 points. A, +1. That means that it's going to be a U shape and it's not going to be too severe or too smooth. B is +3. That tells me it's the vertex is going to be on the negative side of the y value of the y-axis. And finally, C is -4. So one of the parabola arm, or the side of the parabola extending back upwards, is going to cross y at -4. So here's 0, 0, 1, 2, 3, 4. So it will be shaped something like this. Okay. Crosses at 2 points on the x-axis. It's U-shape and it's not too severe, not too smooth. The vertex is on the negative side of y. And the side of the parabola will intersect the y-axis at -4. All right. So now I have everything I need to know to move forward. I know what this thing should be shaped like and where it's located. Okay. There's still some unknowns. I could draw an infinite amount of parabola that meet all these requirements, right? I could do something like this. That, you know, it could be, the vertex could be right by the y-axis. I don't know. It could be something like that. So there's still some unknowns, but I have a general idea of what I'm going to be solving for, okay? That positive discriminant is going to help us too. The next thing you got to do is you got to figure out this vertex. That's going to nail down one more thing about this, this quadratic equation. It's going to tell us where the bottom part of our U is. What is the coordinate of this point right here? Okay, so let's figure that out. The formulas are H equals negative B divided by 2A. They use H, but when you solve for H, you're figuring out the X value. So in your Cartesian graph, your X and your Y, this one's going to figure out your X. Then you figure out your K value, which is essentially going to be your Y. Why they use H and K, I don't know, as opposed to X and Y, but they do. The formula for this will be A times H squared minus B times H plus C. Now notice they're using H in here. So we're going to have to figure out what H is first before we can plug it in, okay? So let's use those two equations. First, let's figure out H. Negative B divided by 2A. And our equation was X squared plus 3X minus 4 equals 0. So negative B would be negative 3. Negative 3 divided by 2 times A, which is positive 1, equals what? Negative 3 divided by 2. That's going to be our X value, okay? Hold on. All right. Got my calculator ready. So, but we can say negative 3 divided by 2 is 1.5, negative 1.5. So our X value of our coordinate of our vertex is going to be negative 5. Okay. Now let's plug that value in to the K. It'll be A times 1.5 squared minus B times 1.5 plus C. So let's plug in our values here. It'd be 1 times 1.5 squared minus 3 times 1.5 plus negative 4. All right, so I'm going to have 1.5 squared. This will be 2.25 minus 1.5 times 3. Going to be negative 4.5 plus a minus 4 is going to be minus 4 equals what? So I have 2.25 minus 4.5 minus 4 equals negative 6.25. So this was my X value of my vertex, and this was my Y value. So now knowing that, I can even further lock down this parabola. Now I know the shape, the severity, location, to the y-axis, how many times it crosses the x, and all that. Now I know the vertex as well, and where it crosses the y. So we already figured out it crosses the y-axis at negative 4. And I also know the vertex is going to be negative 1.5 and negative 6.25. So 5, 6, 7. So it'd be right here somewhere. Okay. So this point is negative 1.5 and negative 6.25. This point is 0 and negative 4. And we know it, we know it's a U shape, so it'll look something like this. Okay. Which is starting to take shape to what we already know. U shape, not too severe, crosses X at 2 points, and it's on, the vertex is on the negative side of X, or negative side of Y, okay? So is everyone following so far?
You are
All right.
good.
All right. So I've kind of gone over these steps one by one in solving this one, but we still need to figure out what our X values are. So where does it cross here and here? We know it crosses it twice, but what are those two values? Okay. All right. So first part is to read the quadratic formula and figure out all the characteristics of it, which is what we've been doing. Okay. The next part is figure out the discriminant, which we did. We found it to be positive 25. We know if it's a positive number, it crosses X twice. If it's 0, it's going to cross it once. And if it's negative, it'll cross it none. But its mirror image will cross it twice. And I'll get into all that. And then the third thing we do is we're going to find, well, I skipped a step. I already found the vertex. But we could find these X values before that vertex, okay? I like to find the vertex first. That way we get that shape and location really nailed down. But how do we solve for these X values? So we did this step. We found out the discriminant. All right, so step 3 was solving for X. So let's do that. X squared plus 3x minus 4 equals 0. All right, let's solve for X here. Well, the best way to do this is to use the roots form of this equation, okay? And we already figured out, I already showed you how we went from this form to the roots form. So we don't need to figure out how to do that part. We already know the roots form is negative b plus or minus square root of b squared minus 4ac divided by 2a. So let's start plugging in our values into this, and we're going to get 2 answers for X. I'll show you why. So negative b would be negative 3 plus or minus square root of b squared. So 3 squared is 9 minus 4 times 1 times negative 4. Be 4 times 1 times negative 4. Divide all that by 2a, which is 2 times 1, which is going to be 2. So let's simplify this and figure out what our values are. Negative 3 plus or minus. We already figured this one out, was 25, remember? 4 times 1 is 4. 4 times negative 4 is negative 16. 9 minus negative 16 is 9 plus 16, which would be 25, divided by 2. Square root of 25 is 5, so we can even go any further. Negative 3 plus or minus 5 divided by 2. All right, we have this plus or minus here. So let's do one with plus and one with negative. Negative 3 plus 5 divided by 2 equals, and negative 3 minus 5 divided by 2 equals. So negative 3 plus 5 will be positive 2 divided by 2 is 1. So that's one of our answers. Negative 3 minus 5 is negative 8 divided by 4. I'm sorry, divided by 2 is going to be negative 4, right? So these are our two values for x. This is where the parabola is going to intersect the x-axis. It's going to intersect it at 1 and negative 4. So, and that's about right. Even for me drawing horribly, it's going to intersect it at 1 and negative 4. 1, 2, 3, 4. So now we have 4 points to draw this parabola. We have the x values, we have the y-intercept, and we have the vertex. All we got to do now is just connect those dots. Okay, so we've solved for the quadratic formula on this one, or that for this quadratic equation. I want to show y'all this. So if we come up here, it's pretty cool. This is just a quadratic quadratic formula calculator and graph. So if I put in our values for this, it'll be 1, 3, and negative 4. So that's our equation, right? A was 1, B was 3, C was 4. It's going to go through. It tells us our x-axis points. It tells us our, let's see. Well, here it is graphed out. So this is exactly what we expected, right? We have our 4 points. We have our vertex point down here, which is correct. What's 25 divided by 4? 25 divided by 4. 6.25, that's right. So they kept theirs in fraction form, but it crosses the y-axis at negative 4, and our two values for the x-axis are negative 4 and 1. It's U-shaped, it's not too severe, it's not too shallow, okay? You can plug whatever you want in this thing. Let's do 100, negative 12, just hypothetical, putting all this stuff in. Positive 9, 89, let's go. All right, so this one, if you work backwards, as you notice, the y-axis is down here. This discriminant does not, this parabola does not cross the x-axis. So that tells me that this discriminant is going to be negative. So let's go back up here and let's figure out what the discriminant for this. I guarantee it's going to be negative though. So the discriminant, if you remember, I'll try to remember my numbers here. Hold on. The discriminant is b squared minus 4ac. So what is this? So b in that equation I just had was negative 12 minus 4 times a, which was 100, times c, which is 89. So let's figure out what this is. 400 times 89. 400 times 89 equals that minus negative. So store 1, negative 12 minus, recall 1. Wait up, I messed up. Oh, I forgot to, hold on. 12 minus, recall 1 equals negative 35,612. negative 35,612. So that tells me it's a negative, so it will not be crossing the x-axis. Okay, so let's use that example. Well, no, that one's kind of big. Let's use another one. I want to show you how to solve for these negatives, okay? When you have a negative discriminant. So before we do that, I guess back to the first equation, we're going to have, I go through and I explain what each one of these values told us about our parabola. And sure enough, it is going to be graphing it properly, okay? The way you check your quadratic formula, okay? So you have your values here. You have your 1 and your 4. How do you know those are right? If you plug a 1 into this equation for x value, it's gonna be equal to 0. And also, if you plug in negative 4 to this same equation, you're gonna get it to equal 0. So there's two values that work and that are true for this equation. Let's try the 1. So it's not x squared, it'll be 1 squared plus 3 times 1 minus 4. Is that true? Does this equal 0? 1 squared is 1 plus 3 minus 4 equals 0. Yes, it does. 1 plus 3 is 4. 4 minus 4 is 0. So that 1 does check out. The next option was negative 4. So let's plug in negative 4 into there and see if it works. Negative 4 squared plus 3 times negative 4 minus 4. Does that equal 0? 4 squared, negative 4 squared is 16 plus negative 12 minus 4 equals 0. 16 plus a negative 12 is 4. 4 minus 4 does in fact equal 0. So that negative 4 does check out as well. Okay, so does everyone understand that, how you check it? You're going to get your x values and you can plug them right back in to see if they're true or not. It's a good idea for a check. Let me make sure this is this is the negative discriminant. So let's take this one and work through the whole process and then we'll be done, okay? 5x squared plus 2x plus 1 equals 0. All right. So in this situation, A is going to be equal to plus 5. B will equal plus 2. And C will equal plus 1. So just from this, we can tell it's going to be a U shape because it's a positive A. It's 5, so the shape's going to be kind of wide. It's not going to be so sharp, okay? B, it's a positive 2, which tells me it's going to be on the negative side of the y-axis. Your x value of your vertex will be negative. And C tells me it's going to cross the y-axis at 1. All right? So not knowing anything else, I know it's going to be shaped something. If this is 1 on the y-axis, it's going to be shaped something kind of like that, okay? But there's one more thing I got to figure out, the discriminant. Are we going to touch the x-axis or not, okay? The diagram I'm showing here, I'm saying I think it does. Let's see if that's true. So the discriminant is b squared minus 4 times a times c. B squared be 2 squared minus 4 times a squared 5, I'm sorry, times 4 times 5 times 1. 4 times 5 times 1. So I'm going to get 4 minus 4 times 5 is 20 times 1 is 20. So I get 4 minus 20 equals negative 16. So I have a negative discriminant. That means my parabola will not cross the the x-axis. So that was wrong. It's going to be shaped something like this instead. Okay. So now we know the shape. We can figure out the vertex, or we could skip it. I'm going to figure it out. Let me see. Okay, so the vertex for this is h first. H is negative b divided by 2a. Negative b is 2. Negative 2 divided by 2 times 5 is 10. So I'm going to have an x value equaling 1/5 or 0.2, right? Let me see. Yeah, 0.2. 0.2 negative. So my vertex x value is going to have 0.2. And to figure out k, which is going to be our y value, it's going to be a minus bh plus c. This should be ah, sorry, squared. Ah squared. So a times, so it'd be 5 times 0.2 negative squared minus b, which is 2 times 0.2 negative plus positive 1 equals what? Do the math, it comes out to be 0.8 equals your y value. So our vertex coordinate is going to be negative 1, negative 0.2, and y is 0.8. And if you notice, sure enough, this is telling me that my vertex is going to be above the x-axis, which is going to be true because it's not going to touch it. It's really close. It's only 0.8 away, but it's not going to make contact with that x-axis, which tells me I do not have any real solutions for this equation. However, its mirror image will have 2 solutions, okay? So let's go and figure out how to solve a quadratic formula's x values if the discriminant is negative. So if I take my 5x squared plus 2x plus 1 equals 0, I'm going to apply the roots value to solve for x. So x will equal negative b plus or minus square root of b squared minus 4ac divided by 2a. Start plugging in my values. X will equal negative b plus or minus square root of b squared minus 4 times 5 times 1 divided by 2a. 2 times 5. If I simplify all this, I'll have negative 2 plus or minus square root. We already figured this out. This whole discriminant was negative 16 divided by 10. Okay? So now I have 2 options, the plus option and the minus option. It'll be -2 plus square root of -16 divided by 10, -2 minus square root of -16 divided by 10. As you notice, we have a problem. We're taking the square root of a negative number, which is impossible, right? So this is going to result in a complex solution, a not real solution. And I have it here. The complex solutions are not real. The solutions are imaginary. They're called imaginary. Imaginary numbers cannot be graphed, but the mirror image of the solutions can be. In other words, if you have a U shape, it can be inverted to a frown shape or an N shape. Then the solutions would intersect the x-axis. To flip the shape, simply remove the I from the solution you get and solve. In this case, all right, let's go up and solve them. So if I do this, I get, if I did -2 plus square root of -16 divided by 10, and this will be -2 minus square root of -16 divided by 10. Okay. So to make it imaginary, you just do the square root of the number, void out in your mind the negative sign. So square root of 16 is going to be 4, but it's a negative number. So it's not just plain 4, it's going to be 4i. Okay. So what you have here is -2 plus 4i divided by 10. If I divide the 10 by 2 and the 4, I can simplify this to say -0.2 plus 0.4i. Let me rewrite it bigger. -0.2 plus 0.4i. Okay. Down here, you get -0.2 minus 0.4i. So these are my two solutions. Even though they're not real and they're quote unquote imaginary, they are the solutions for this quadratic formula. Now, what this was saying was, if you just simply take out the I and you solve this, it's going to give you a value, and that value will be the X value with the mirror image in mind. So this -0.2 plus 0.4i, just think of it as -0.2 plus 0.4. If you do that, you're going to get 0.2 as the answer. Well, that's going to be one location. 0.2 would be a location that my inverted mirror image parabola would cross the x-axis. Same thing with this. -0.2 minus 0.4i. Think of it as -0.2 minus 0.4. If you do that, you get -0.6. So now my mirror image parabola is going to cross the x-axis at 0.2 and -0.6. So this point right here would be 0.2, and this one would be -0.6. Okay. Yeah, it's not our parabola, but it's a perfect mirror image. And if we know that, then we can go and solve the rest of it. Okay. Or not solve, we know what it's shaped like, right? So we figured out the vertex. Now for the check. I'll end with the hardest part. So we have, let me write it, 5x squared plus 2x plus 1. All right. And we found out that we had two solutions. One of them was 0.2 plus 0.4, -0.2 plus 0.4i. That was one of the results we got from inserting our values into the roots formula. Okay. So if I plug this in for every time I see X and solve for this equation, that's going to give me a zero number. A zero equaling zero. So it looks something kind of like this. 5, I'm not writing X, I'm writing this now. Negative 0.2 plus 0.4i squared plus 2 times negative 0.2 plus 0.4i plus 1 equals 0. So this is what I'm going to be solving for, okay? I'm not going to bore you with all the distribution and all that. If you look at my blue screen, you can see that I do work my way down and I do end up getting 0 equals 0. The caveat in here is if you have, when you're doing all your math, when you have I equaling I equals, by definition, imaginary number, I equals square root of -1. That's what I is, okay? That's why when we had -16, square root of -16, it was equal to -4 squared. I'm sorry, -4i, right? And then we divided by 10, but shoot, nope, not -4. It's 4i. If you did, this is really 4 times the square root of -1. That's really what this is saying, okay? Well, if you square, if you do, so if this is true, then what does I squared equal? Well, that would equal -1 because I'm squaring this. Square root of -1 squared is going to be -1. I'm just removing the square root. So I squared, when I work my math all the way through this and I see an I squared, I can remove that I squared and I can replace it with a -1. And that's what I did here. When we do this, we will get 0 equals 0. So that is a check, okay? Are there any questions or comments?
You sure you want to ask that too?
Yeah.
Can you show the other side of the sheet? I didn't get a good screenshot. Sorry.
Of what? This right here?
Yes. Thank
Okay.
you.
Yeah. I don't know if you can make this available to everyone.
Yes, I will.
But
Yep.
I can definitely make it available. Did I give it to you already?
No, this one I don't have yet. Nope. So
Okay.
yeah, if you'll
I'll
send it to me later tonight or whatever. My plan is get this out by Wednesday. So
okay.
I'll get it loaded and then out this week. So
All right. Yeah, I'll get it going. I'll give it to you.
no worries.
Is there anyone else? Any corrections anyone saw for me?
Jerry threw in the chat, plus or minus infinity isn't big enough. We need imaginary numbers too.
Yeah. You can explain yourself if you want. I do have these examples in my book too. But I'm going to give it to Trent so that we can disperse it out. Okay.
That'd be perfect.
All right.
That's not it's not easy to topic to one to do over Zoom, but you pulled it off like a champ as always. So
I tried it. That thinking about maybe voiding the conversion from typical to root. I could do away with that. I just want to show y'all that it is possible, and that's how you get from one to the other.
Right. It's good stuff.
Okay.
Looks like George is typing. Let's see what George
Okay.
has to say. Or you can unmute George if you already hit send. Not so much.
High school was a long time ago.
Oh yeah, exactly. For
Yeah.
sure. Yeah, no, this is something that, I mean, you have to do a lot and a lot. I mean, it can be mind numbing for sure, but
I've been putting together a presentation. It's kind of short, Trent, but it's on PIMDIS.
okay. Yeah.
Just really, really going through those algebraic operations. You know what I mean?
Yeah, that'd be
And,
fantastic. Yeah.
It's not very long, but man, that to me, that you should brush up on that before you go take any kind of survey test, just to make sure you're doing those exponents before you do your addition, subtraction, or whatever the case may be. I'm more than willing to go over that one with y'all once.
Okay. Yeah, for sure. Rob, go for it, Rob.
Yeah, great job, Dane. And this is one of those topics that is so brutal in the hardcore algebra that we can kind of just fry our brains watching this and go, man, when am I ever going to use this? But there are times when the easiest solution to a problem is to develop an equation that describes what you're trying to do to solve for that X.
Yeah.
And once you create the equation, then you throw it into the quadratic formula and crank it right out. It's that stuff that I think it was George that said high school was a long time ago, but it's one of those things when you look at this and you go, when would I ever use this? This is nuts. But solving simultaneous equations is another one that you end up setting your equation to 0 and solve for X to come up with things like slope intercepts.
Yeah, I was about to say, you took the words out of my mouth. Slope intercept is a perfect example of that. I could do that one too, Trent. If you want to write that down as a a topic, that's a good one. And that one actually, you can see it as a surveyor why the hell it would apply. This is a stretch, but
well, of course, the parabolics is going to be vertical curves.
Yeah.
And you can also use the quadratic if you have some kind of problem where the problem states, I remember one from an exam many years ago where we had to find the elevation of a pad, and they didn't give you enough information to just do the calculation straightforward. But one of the things that they had was the front yard and the rear yard had to be the same dimension front to back.
okay.
So you'd come up a slope, and then from that top of slope, then you'd have it was like a 2% to the edge of the pad. And then the pad was supposed to be 40 feet across. And then in the rear yard, you'd have that same dimension as the front at a 2% draining towards the rear, and then the toe of a slope and on up to a fixed elevation at the top. And, it was one of those things where I looked at this and said, I don't have enough information, except I can say that here's, 2 X values, and crank it through a quadratic formula to come up with with the distance that that X represented. And then
Right.
from that, solve for the elevation value.
Yeah, those
Yeah.
I was gonna say those are the good ones when you can take some real world stuff like that and back it into formulas like this. That'd be cool.
Yep. Yeah, I know that would be a good exercise to add to this, to show like a real life problem, you know?
Exactly, for sure.
Well, I did go over and I apologize for that, but
Oh no, you're right on time. It's perfect.
okay. I appreciate y'all patience and yeah, Trent, put me down PEMDAS and intersection, the calculation of intersection.
Yes, sir. I will put those down for sure.
All right.
I love it. Anybody got any more questions they want to talk to Dane about? Maybe nothing. If not, I'll throw your contact information and your email in there as well, and people can reach back out to you that way too. So
Yeah, feel free. Anyone.
awesome.
All right. Thanks, guys.
All right. Have a good night. Have a good week, everybody.
Yep. Y'all
Hey,
too.
guys. See ya.
Bye, everybody.